I recently started here as a research fellow, and before that I was a PhD student at University of Oxford, and so I'm going to use this opportunity to talk a bit about some of the stuff I did over the course of my thesis, I think. And so this is automatic inference for higher order probabilistic programs, and so I'm going to talk a bit about what probabilistic programs are and what higher order probabilistic programs are, and then talk a little maybe about how we could do automatic inference. So here's kind of a picture of what data science looks like today for a lot of practitioners in practice. You have some data, and you have some kind of prediction task you want to do, say clustering. So you're like, okay, how do I do clustering? Well, one way that you can do clustering is you can say, okay, here's a model which encodes some assumptions. I say maybe my data Y is roughly distributed as a mixture of normal distributions with unknown mean and covariance matrices. So this is a model for clustering, and if you're familiar with this model, you know that you can fit this model by doing techniques like Gibbs sampling or variational Bayes, and those work pretty well. And so for model is kind of an overloaded word in machine learning, but when I say model, I'm going to mean generative models or latent variable models, where you can do something like in this middle figure here, where you can simulate synthetic data and kind of get an idea for what the model looks like. And so then here on the right, we've fit the model to the data on the left, and we're like, well, you know, of the world of all possible generated clusters of data, this is the world of clusters of data of means and covariances that fits well with what I have. So this is how do you do this, right? So this may be chosen by somebody who's familiar with the domain at hand. Then this requires somebody who's familiar with algorithms for doing statistical inference. And these things are generally then packaged up all together and shipped as machine learning software. So one part is the model, and one part is the model-specific inference. And so, for example, for this model, there's a module in scikit-learn which will go do variational Bayes inference for you and tell you, hey, here are some clusters. You press go, and you're golden. But when you're not golden is if actually, you know, maybe these aren't the right assumptions for the kind of clustering that I want to do. Maybe I know that a Gaussian model for my data, a Gaussian noise model makes no sense, or maybe, or whatever it may be. And as soon as you want to change something, once you change the model, once you change the math, then you need to rechange and rederive and recode and retest this sort of model-specific inference code. And for anyone in the room who's done this, you know, this is annoying. This takes a while. This you sit down in an afternoon and are like, yeah, I have a good idea what the model is. Or maybe you talk to somebody who knows the domain. It's like, hey, I know what the model is. And then you spend like 2 weeks testing your code to make sure it actually works. So the promise of probabilistic programming is to kind of move past this in some way by introducing an abstraction barrier between modeling and inference. So like, what if it's possible to say, I'm going to define a modeling language, some kind of domain-specific language, in which you can write down a probabilistic model, in which you can write down a generative model. Then with that as an abstraction barrier, I can code up an inference backend, which is in some sense model agnostic and can do inference on any model written in the language. Or if I go and want to change my model, as long as I can write the model in the language I'm provided, then hopefully the inference backend will be able to handle my model. So this is the goal. And you can think of probabilistic programming as something like statistics for programs. So if you think of normal computer programming, you have some algorithm. And the algorithm produces an output. And the output there on the left is the thing that you care about. You just wrote some code to generate the output. And if you think about statistics, you have this sort of inverse problem. So you have a model, it generates some data, and what you're doing is inference running backwards to say, okay, well, I really care about the distribution or the values of these random variables or these inputs to the model. In probabilistic programming, what you do is you say, well, here's a model, here's an algorithm, and I'm going to suppose this program, this small bit of code that I just wrote, could hypothetically have generated my data. And given this program and some data, then tell me what are the inputs into this program? Or if it's a stochastic program that samples over the course of it, what path did it take through the control flow of this program? And so on. This isn't a new idea. This has been done by a bunch of people from programming language, machine learning, statistics communities for a while, but I'm going to talk about a couple little subsets that I think are particularly interesting. So one way I think of as calling it sort of inference first. And so if you're doing this, you start by saying, you know, I have an inference algorithm that I know and love, and I know when it works, and I've coded it up, I've tested it, I really don't want to have to write this again. And so what I'm going to do is I'm going to start with Gibbs sampling and say, I know this works on finite graphical models. like directed graphical models, I know how to give samples. So I'm going to go design a domain-specific language that restricts what I can write such that I know I can have a give sample of the functions. You might say the same for Hamiltonian Monte Carlo and say, well, then I better restrict my language to something which only has continuous latent variables so that I can take gradients through my model, and in a language that I can run auto-differentiation on so that I can compute these gradients automatically, and so on. Same with expectation propagation is a great inference algorithm. You say, start with this, I know it can run on factor graphs, so I define a language which restricts me to finite composition of factors. And this gives you languages like Bug, Stan, and Infer.net. The other sort of approach, so you might ask, okay, great, that's great, we're done, right? The other sort of approach, though, might be to go kind of language first. So are these language restrictions actually restricting? And in some sense, they are. Like, in order to say, for a lot of languages that start this way, inference works kind of as long as you assume you can really kind of keep track of how many random variables might ever occur and where they are, and so on. So like in a lot of these languages, you'll have things like if you have a for loop, the endpoint of the for loop has to be deterministic. You can't have a random number of random variables inside a for loop, or all of a sudden you have something that looks like a Bayesian non-parametric model and it's out of the scope of this inference language that you just wrote down, and so on. So the other way you can go about this is say, well, I'm going to start with an existing programming language, something which I know I can write code in, and maybe I even have simulator code sitting around in, and ask the question, if I do this, can I do inference at all? So one way we can go about this, so here's a very simple program. This is written in the Anglican probabilistic programming language, which is essentially Clojure, which is a scheme-like language that runs on the JVM, and you can transparently call all Java code, and you can interact with other languages if you want, with two added special forms, primarily two. One is sample, which takes a distribution, and as the user, it semantically returns a random value sampled from that distribution. And the other is observe, which returns nothing, but taking in a distribution and a value says, if I were to run this program semantically, condition it on this having happened. So here's a sort of standard coin flip type model. So that there's a coin that comes up heads with some probability, and you don't know what it is. And so you say, that's the bias of the coin. And so you flip this coin, and that's your likelihood distribution. And then we observe 3 times that this flip, which returns true, false, comes up true. And this says, and then we predict, we return the value of bias. And so what this says is, well, you know, of all the possible executions you could get from simulating, from sampling from this beta distribution, a bias term between 0 and 1, give me ones which are, in some sense, consistent with observing that when I flip that coin, it comes up true 3 times. And it turns out with just sample and observe as your interface between the language itself and your inference backend, there's a lot of inference algorithms you can kind of write. You can write sequential Monte Carlo algorithms. You can write single-site Metropolis Hastings algorithms. This is sort of like a Metropolis within Gibbs type algorithm. You can write down particle MCMC algorithms and more. And you can think of this then as doing Bayesian statistics over programs. So this is a silly program to bother writing in a language which gives you no restrictions. But here's the kind of sort of fun thing you can imagine doing. And so here, we're dropping in balls on the left, and they fall down. And there's a box over here on the right. And this is calling a Java physics simulator, which is the physics simulator used for Angry Birds. It's a 2D physics engine. And so say, what if you wanted to imagine a world where something happens where when you drop these balls on the left, 20% of them land in this box on the right? So you can say, well, you know, I could add in sample statements that construct possible worlds. And so then when you run this, so we say like, okay, there's a random number of bumpers, there's random locations for where they show up, and simulate. And they bounce around, and they go places, and they fall down. So if you want to turn this into a statistics problem, you say, well, I'm going to observe that of those 20 balls I just dropped in, approximately 4 of them ended up landing in the box. So if you run it now and just run inference, you get samples out where approximately 4 of them end up going in. And in doing this, they bounce off of each other in kind of crazy ways to kind of obtain this. And so these are in some sense posterior samples conditioning on approximately 20% of the balls landing in the box at the end. And that's sort of like a weird model to imagine writing down as equations. And for this one, maybe since there's not much in the middle, you could imagine writing down a MCMC sampler by hand or doing an ABC type algorithm. But that's work. This, you just write the simulator and say observe. So how does this work? Like, how is this possible? So here's an example inference algorithm that you could run. So this is a schematic kind of for how you could implement sequential Monte Carlo using just sample and observe as the way your inference backend interacts with a running program. So you start by running, say, L different copies of the program represented by blue dots. And you run them forward until you hit an observe statement. And if you hit a sample statement, you just simulate. And so then at this observe statement, you compute a probability. And then you say, well, you know, some of these are good and some of these are bad, and I'm just going to go duplicate the ones that run well and kill off the ones that don't. This is sort of standard SMC, only what we have now is each one of these is a running program, and you've duplicated copies of currently running programs according to how well they match the observe. And you can just continue doing this, and at each new observe, maybe you've sampled things in between, maybe you haven't, and at every observe, you kind of weight by how well it goes, and as you run to the end, you end up with some set of executions of the program which have finished, and these kind of represent the posterior. So you can take the value of bias, you can take the location of the bumpers in the programs that reached the end, and use these as samples. And you can run this whole thing over and over again if you want, and there's other algorithms as well, but just as an idea. The funny part here, if you think about running a computer program, is we just duplicated a running computer program and executed it from the same point on a whole bunch of times. So when we got here, we were like, OK, this is good so far. I want to run it again, not just continuing once, but I want to basically duplicate my current program state and run it multiple times. And this might sound painful, but there's some nice ways of doing this. One amusing way is you can just use standard operating system primitives. So in Unix, there's a command called fork, which basically clones any currently running process. You may be mostly familiar with it as kind of a way of doing denial of service attacks on machines, where you show up, you just call fork constantly, and it spawns a whole bunch of extra processes that just use up all your resources, and you're in trouble. But like, actually, if you're running inference, then this is kind of what you want. You want to fork bomb your machine and take the executions that are going well and clone them over and over again and kill off the ones that don't. And so this is maybe not the most, so fork is a pretty, it's not bad. It works. It's a bit heavyweight as a way of cloning processes. You have to clone an entire process, but other people have kind of followed up on this since, and there's some people at Cambridge who have a version that runs in user space, which is a couple order of magnitudes faster, but has the same property where it copies it in a lazy manner. So you don't have to go and rerun the entire program every time. You don't have to deep copy all the memory. It's basically the idea of how operating systems do memory management for copying processes is something you can leverage for inference. One thing that came up as a response to doing this is if you think about what happened when we ran that sequential Monte Carlo algorithm, how much is parallelizable? So you can parallelize simulating your program forward, but when each program hits an observation, so when it hits one of these likelihood evaluations here, you have to wait in a sequential Monte Carlo algorithm for everybody to see, am I good, am I bad, did I do well, are my sampled variables good sampled random variables? And that's a global blocking operation. So kind of looking at that, we were sort of inspired to try to come up with a way of removing that. So we have an algorithm called the particle cascade, which basically does this asynchronously. And so every particle arrives, and instead of each execution of the program, instead of looking at all the other executions that you're running simultaneously, it just looks at what executions have reached here so far. And then it makes a local branching decision depending on this. So here I have a video. So imagine you're just running inference on a state space model, think linear dynamical system or Kalman filter. So these green dots are data points, and the gray is the actual kind of posterior distribution, and think of it as a tracking problem. So if you run sequential Monte Carlo, the blue here are currently running particles, and the orange ones are particles which have died off, that have been removed because they don't really, they're not very good. They're not consistent with the data anymore. So you propose kind of broadly. Some of them look good, and here you are. I mean, you can see what's happening, right? And you get to the end, and some of them end up representing your posterior approximation. For particle cascade, it's kind of a different sort of property. You just keep launching particles forever. This is slowed down here, and then some of them eventually start reaching the end, and as they start reaching the end, it starts to get better and better. And so as you do this, as you do this, gradually it stops exploring dumb parts of the space and goes into good parts of the space, and it does this in a way which you can just keep running more particles over and over and over again, given the ones you already have. And so part of why I think this is fun is this is a new kind of Monte Carlo algorithm where we were inspired to do it because of problems we ran into doing probabilistic programming, and it's actually now an inference method you can use for anything that you write in one of these probabilistic programming languages. And so this is, I don't know, I thought this was nice. Sometimes, so I guess to talk a bit about a couple of other things before, people often complain about Monte Carlo inference. So you can also write things like variational Bayes type algorithms in Anglican language using just this sort of interface as well. And this, you can do this by, so the idea behind variational Bayes algorithms is instead of simulation, you say a simulation and having samples represent your posterior, you say, well, I'm going to define some approximating family which I'm going to fit to roughly represent my posterior, and I'm going to learn the parameters of this approximating family. So here's Bayes' rule. You have your data and your latents, and the true posterior you might get through MCMC simulation is like this. And so we're going to say, well, let's just fix a family Q and learn a parameter lambda such that our Q is approximately the posterior. And then we'll have an artifact which represents the posterior distribution given this data. So the way you can do this is defining a variational lower bound, and you can optimize this with respect to lambda. And I won't go into that except for to say that it's possible to optimize this with respect to lambda just by using sample and observe, by using methods based on policy gradient methods for reinforcement learning, effectively. So you can run the program forward, and when you run the program forward, you can compute gradients with respect to your Q, and you can use this Q, this approximation, as a proposal mechanism instead of sampling from whatever distribution you define in the model. You can sample from this distribution that you're learning. And so an example of us using this for something sort of fun is using probabilistic programs as agents for traversing a graph. So the Canadian traveler problem is this noisy graph traversal type problem. So you start at the green dot and you go to the red dot, and you know, here's the map. It looks like this, and you travel along these things. What you don't know is which roads may be closed. So when you get to any intersection, you can see, oh man, this road is snowed over and you can't pass. So this is why it's called the Canadian traveler problem. Though people from Canada tell me that this is ridiculous because Canada has very good snow clearance. So it's more like an issue with, I don't know, the American and winter traveler problem. But anyway, it's so if you imagine a policy as being depth first search, you could run depth first search from the green dot to the red dot. But depth first search has a kind of free parameter to it, which is which order do I go next? So at every intersection, so depth first search will find you a path, but it's not really going to guarantee you finding you a good path. It's just going to pick, basically arbitrarily, how do I move from here to somewhere else? And so if you imagine saying, well, I would like to, given all the possible instances of this graph, take my depth first search, which is going to represent an agent traversing this graph, and say, learn a distribution over what choice to make at every node in this graph. After you're learning these sorts of preferences, you learn an agent which has pretty good heuristics for where to travel when. And so if you give it new graph instances, it has a reasonably good idea, where should I go given the roads that I have open now. And actually, the heuristic looks a lot like what's known to be a very good heuristic for this problem, which is the optimistic policy, where the agent just always assumes, well, if everything else is unblocked, let's go that way. So related to this, let's think a bit about what we just did. So we had we had an idea where at every one of these kind of sample statements, instead of sampling from the distribution we're handed, we're going to learn an approximating distribution which samples from something that more closely resembles the actual posterior, given that these come out true. So that's fine, but that Q here now is specifically tailored to given this particular value of y. And so if I have a model that I might want to use over and over again, and think about the machine learning software in the first slide for doing clustering, you really don't want to have to go then learn this every time. You want something where, like, if I give you new data, I give you a new approximation. And so this is kind of the idea of amortization of inference. So compiling away the runtime costs of doing inference. And a way to think about that is if you have something here, so this sort of looks like a regression model. This generates your data. But you can imagine an inverse model which takes all these arrows in the graph and flips them backwards. So instead of starting from latent variables and simulating your data, it takes the data and simulates the latent variables. But of course, you don't know what the functions are along any of these arrows. It's just kind of hopeless. But maybe we could learn them. And so one way you can think about trying to learn them is taking this scale divergence, which measures the difference between our posterior pi and our approximating model Q. And this is for a single data set. You can minimize with respect to lambda to learn a good approximating Q. And if you're familiar with these things or looking closely, you'll see that my pi and my Q are backwards from before. And this is if you're learning important sampling proposals, then this scale divergence has better properties than the other ones. But so if you imagine, OK, well, we might get many, many, many data sets. Instead of just fitting these parameters of my approximating model, let's define a function phi from some upper level parameters and the data, and have these produce our parameters, and then minimize with respect to these upper level parameters in expectation over all possible data sets. And so if you trust your generative model, this is actually possible and easy. You can think about all possible data sets under your defined model here, because you can simulate synthetic data. So you start from these. You can simulate possible z's, t's, and so on, and use these to just compute these via stochastic gradient descent. And so then fix this to be something like your favorite neural network model, and you've learned inference software. So here's kind of an example for that toy model on the previous slide. You say, OK, well, here's some data, the data being the black dots. And this is a non-conjugate polynomial regression model. So it's got like student t likelihoods and Laplace priors on the few weights for linear and quadratic terms and intercept terms. So you can see this is a kind of model. It's a fairly diffuse prior. Here's some data that was never encountered during training. And if you run Metropolis Hastings on this, you end up with a posterior that looks kind of like so. If you simply plug in the value of y into this learned artifact, you get out estimates of the posterior distribution, which look reasonably close. And you can then use this as an important sampling proposal or an SMC proposal if you want to refine it to something that actually looks right. And like this here is fundamentally an iterative algorithm. You have to run it for a while. And this here is sort of fundamentally feed forward. You give it data, and it pushes out an answer. And the amount of work to learn the neural network proposal is much more than it takes to run Metropolis Hastings on a single data set. But if you're in a scheme where you would like to do inference in the same model many, many times, maybe it's like an online monitoring type system or so on, then this may well be worth it. So I guess saying a little more about this, there's some fun things that happen if you have structure in your model. Say it's a hierarchical model, then you can exploit that in structure in your approximation to learn something which doesn't have to invert the entire model all at once. It can invert just sort of individual local factors, and you can use this within SMC. And in sequential models, such as a factorial HMM, for example, you recover something which can look familiar as resembling the optimal proposal distribution for sequential Monte Carlo and these types of models. And we have some kind of promising initial results for this, and we're looking at what to do with it next, I think. So if you want to try out probabilistic programming, I think So the language Anglican is one that being developed at Oxford that I contributed to during my PhD. It's got a fairly decent language reference and a bunch of examples which are online as web documents that you can view. Last summer, 3 of us ran a summer school course in Portland, which has slides and presentations that kind of really walk through all of it, and a bunch of exercises. And they're exercises that you can run in web-based notebooks you can run in the browser locally. So it's pretty user-friendly types of exercises for learning this. And also you can email me or find me. I'm in one of the offices down the hall. And also I believe Frank Wood is actually giving a tutorial in one of the masterclass sessions coming up on Anglican and probabilistic programming in the next couple of weeks. I don't remember the exact date. So okay, yeah, thank you. These are all the collaborators for the various things. This is and Frank was my supervisor.